Hello everyone, my name is Phongtharin from IBM Research. Today, I will be representing my team to present our work on the topic of detections of anomalous sound for machine condition monitoring using a classification confidence. We also submit this work to the DCASE Challenge Task 2 this year, where we actually obtained the 4th ranking in the total team ranking. First, let me start the presentation by recapping you with the description of the task. Given the input sound for the machine, we would like to build a model to identify whether the sound is a normal or an anomaly sound of the machine. One important aspect of this task is that it's actually an unsupervised task, which means that only a normal sound is provided as a training data. This makes the problem cannot be solved easily using a two-class classification techniques. The organizers actually provide a data set that contain multiple machine type and machine ID. The training data only contain the normal sounds, while the testing data contain normal and anomaly sounds. Both training data and the testing data contain an additional information, which is a label that identifies the sound with which machine type and ID is actually belong to. The role of the participant is to build a model to detect anomaly for each of these machine type and ID. AUC and the partial AUC is used as a matrix. In this work, we'll use deep learning as a main approach. There are two categories of the deep learning approach for anomaly detection. The first one is called reconstruction-based approach, where we learn the neural network to reconstruct the normal input. Then we try to calculate the reconstruction error, which is the difference between the original input and the reconstructed input, and use it as an anomaly score. An example of these techniques is autoencoders and GAN. The second category of this category is the feature learning based approach. In this approach, we learn the neural network to map an input from the sound space to some feature space where the normal and anomaly sound can be separated easily. Then in that space, we calculate some distance and use it as an anomaly score. An example of the techniques of this approach is a deep one-class classifications. One variation that have been used is the outlier detections of the classifier. By using it, we build the classifier and then use the classifier confidence as an anomaly score. In this work, we also focus on these variations. Since we would like to use a classification confidence as anomaly score, the question is how we're going to build the classifier. In this work, we propose two approaches. The first one is we build the classifier using a supervised learning by using a machine type and the ID as class label. The second approach is where we use the classifier, we build the classifier using the self-supervised learning, where we actually generate the pseudo label using the type of using various type of acoustic transform. After we get the anomaly score from each approach, then we try to combine it using the ensemble methods to enhance the performance of the anomaly detection. Next, let me explain our proposed method in detail. In the first approach, where we train the classifier using the machine type and ID as class label, we gather all the normal data of all machine type and ID and use them as a training data. Data from different machine type and ID are treated as different classes. After the classifier is trained, the test sound is passed through it, and we calculate its normality score using the classification confidence. There are two choices for this. The first one to use the maximum softmax probability, or the MSP, and the second one is to use the softmax probability considered class label of the test sample. For example, if the test sounds come from the class sliders and the prediction from the classifier is shown to the right, then SP will be equal to 0.5, where the softmax with prior will be equal to 0.3 because the test sound is come from the class sliders. The anomaly score can be calculated from the equations 1 minus normality score. In the second approach, we trained the classifier using the pseudo label, where we generated using different types of acoustic transformations. This is resembled to the anomaly detection techniques in image space, where we generate a pseudo label and train the classifier using the geometric transformations. In this approach, we gather all the normal data of one machine IDs of one machine type, and then we apply 9 types of acoustic transformations, which is a combination of three different parameter sets of pitch shifting and 3 different parameter sets of the time stretchings. After applying these acoustic transformations to the normal sound, we use all the transform sounds to train the 9-class classifier. A data that generated from different transform will be considered as a different pseudo classes. During inference, after the classifier is trained with the pseudo label, we apply all types of acoustic transform to the test sounds and then use the classifier to predict their softmax probabilities. Then the normality score of the test sounds can be considered as the average of the softmax probability of all transform samples, consider their type of transform as a prior. For example, if the test sound is transformed into the AT0 and passed through the classifier, and the softmax probability is shown in the top row, we only consider 0.71 labeled in yellow, and for the AT1, we consider 0.58 labeled in yellow, so on and so forth. And then the anomaly score is calculated as the average of those softmax probability labeled in yellow. And similarly, for the anomaly score, we can calculate using equation 1 minus normality score. In our proposed method, we also use other technique to improve the performance of anomaly detection. The first technique is to use the sound segment. Instead of passing through the whole sound clip, 10-second sound clip, to the neural network, instead we cut this sound clip into small sound segments and then pass it to the neural network. This based on the assumptions that anomaly usually occur only within a small part of the sound clips, and this will make the neural network to be sensible to more to the anomaly. By doing this, it also help increasing the training data, which make the training of the neural network become more robust. And during the inference, after we calculate the anomaly score of its segment, we take the average score of its segments as the anomaly score of the whole clips. The next techniques that we use to improve the performance is called the center loss. In anomaly detections, a good feature learning usually for anomaly detection usually require 2 types of losses. The first one is descriptiveness loss, and the second one is compactness loss. Cross entropy when we train the classifier can be considered as descriptiveness loss. And here we introduce the center loss, which is equivalent to the compactness loss. The center loss is defined as the equation written here, where xi is the deep features at the specific layers of the network. Then cy1 is the center of the deep features of the sample in class y1, and this is updated or calculated based on each mini batches. So this center loss is actually equivalent to the distance in the feature space to its center of that deep feature space. Then we use this center loss combined with the cross entropy to train the neural network. By using this center loss, it will help minimize the inter-class value and distance and make the class become more compact. In the last approach that we use to improve the performance of the anomaly detection is the assemble methods. In our assemble method, we have 2 steps. In the first steps is to normalize the range of the anomaly score of all model to the range 0 to 1. This can be done by fitting the distribution using anomaly score from the normal sample in the training data. In this case, we use gamma distribution. And after the distribution is fit, we can calculate the normalized anomaly score, which range between 0 and 1 by using the cumulative distribution function or the CDF. After the anomaly score of each model is normalized, we ensemble them by using the probabilistic aggregations as shown in the equations below. And FIX is represent an anomaly score of each submodel, where the FEX is the final anomaly score that have been combined. Next, let me explain the experimental setups and the result. In this work, we use two neural network architectures, both of which use log-mail spectrogram as an input, followed by the CNN either on the frequency axis or the time axis. And then at some point, we will do a global map pooling. The important remark of these two architectures is that their number of parameters is very low, especially the one on the right, which only contain only 27K parameters. We also perform the hyperparameter tuning intensively. We use the performance AUC and the PAUC on the test data of the development set to choose the appropriate parameters. The detail of the parameter can be found in the papers. In this challenge, we are allowed to submit 4 systems, 2 of which are the assemble methods, and the other 2 is the system, the methods that we explained earlier. System 3 is the method that uses a classifier trained from the machine type and ID as a class label. It provides the AUC more than 90% in most machines except the toy conveyors. This is because the toy conveyor sounds are very distinct from other sounds, and it causes the classifier not to be so sensitive to small change in anomaly sample. The system number 4, where we train the classifier using the Zulu label, also provide a higher AUC than the baseline in our machine type, and also pretty high AUC, more than 90%, except the toy conveyors and the fan. Using the segment instead of the clips and also the center loss also improve the AUC of our machine type. The ensemble method, which is a system 2, 1, and 2, show better overall performance compared to the standalone system number 3 and 4. As for the challenge result, first, let's consider the system length, where we have a total of 117 systems. Our submitted system get the ranking to 7, 8, 16, and 17. The best system is the system 2, which is an assemble method using the normalized anomaly score. Another result of the challenge is the team ranking. When considered the metrics of the challenge, which is the average of the length of each machine type, we become the 4th rank among the 40 teams. However, if we actually consider the average of the AUC and the PAUC on the evaluation set as a matrix, you can see on the right table that the proposed method becomes the rank 1. Lastly, let me conclude the talk. We propose a method to solve unsupervised anomaly detection for acoustic data. The model is trained using only normal data without using any external information. The proposed method has 2 approaches that use classification confidence as anomaly score. The first approach trains the classifier using the machine type and ID as a label. And the second approach uses the type of acoustic transformations as a pseudo label. We combine the 2 approaches using the probabilistic aggregation assemble methods, and the proposed system show competitive performance in the DCASE competition. Thank you for your kind attention.